In this video, we are going to discuss problem based on infinitely long charged wire using Gauss's law. Question 2.60. An infinitely long charged wire produces an electric field of magnitude 1.23 times 10 to the power 3 Newton per coulomb at a distance of 50 centimeter perpendicular to the wire. The direction of electric field is towards the wire. We need to find what is the charge distribution and how many electrons per unit length are on the wire. So here we have an infinitely long wire that has an electric field of magnitude E equals 1.23 times 10 to the power 3 Newton per coulomb, 50 centimeter from the wire. So I will write this distance 50 centimeter as R equals 50. We will convert this centimeter to meter by dividing this number by 100, so that becomes 0.5 meter. The direction of electric field is towards the wire in this manner. And since the electric field is directed towards the wire, we understand that the charge on the wire has to be negative. Because electric field begins from the positive charge, they go away from the positive charge and end on the negative charge. We need to find the charge distribution, that is lambda, for the wire. Since this is a long wire, it has linear charge density, and linear charge density here is lambda. To find this charge distribution, we are going to first construct a Gaussian surface. And since this is a long wire which has cylindrical symmetry, we will construct a cylindrical Gaussian surface like this. This Gaussian surface is through a point which is at a perpendicular distance of 50 centimeter, which is R, from the wire. After we construct the Gaussian surface, we have to show the direction of electric field vector and the area vector. Electric field is already shown here in the figure. Area vector is always perpendicular to the surface and directed outward. So for this cylindrical Gaussian surface, we have three regions of surface area. Two are this flat circular surface, this is one and this is two. And one is the curved surface here. We have to show area vector pointing outwards through this surface and perpendicular to them. So this is the area vector. We call this A1, A2, and A3. After we construct the Gaussian surface and show directions of electric field and area vector, now we are going to calculate the total flux through the Gaussian surface. Total flux through the surface can be written as sum of flux through surface 1 plus flux through surface 2 plus flux through surface 3. Since electric flux is a scalar quantity, I can find the total flux by just adding flux through all surfaces. We know from the definition of flux, electric flux phi is equal to EA cosine theta. So that is what we are going to substitute here for all the values of flux phi1, phi2, and phi3. For phi1, I write E A1 cosine theta 1. Similarly, for phi2, we write E A2 cosine theta 2, and phi3 E A3 cosine theta 3, where theta is the angle between electric field and area vector. Now, if you look at the figure, area 1 and area 2 are perpendicular to the electric field. Because my electric field is along the y-axis pointing towards the wire, whereas both area vectors are along the x-axis. So they form an angle of 90 degree between them, and we know that cosine 90 is equal to 0. So flux through surface 1 and surface 2 will come out to be 0 for us. And the only flux that we will be left with is the flux through the third surface, the curved region here. Because here the area vector and electric field are making an angle of theta equals 180 degree. They are both opposite to each other and they are making an angle of 180. So I write my expression for flux as phi equals EA cosine 180. I will drop the 3 from area vector 3 because flux through area 1 and area 2 is 0. The only surface where we have flux passing through is A3. And since it's the only surface, I'm just going to write the area as A. We know cosine 180 is negative 1. So here the flux becomes negative E into A. I write this as equation 1. After we find the total flux through the surface, now I'm going to use Gauss's law. Gauss's law says that total flux through a closed surface is numerically equal to the charged enclosed by the surface over epsilon naught. So here we are going to substitute the value of flux we calculated in equation 1. I will write phi equals negative E into A equals charged enclosed over epsilon naught. I need to find what is the value of lambda, which is the charge distribution. And we know how lambda and Q are related to each other. We have lambda to be equal to charge per unit length. So I can write the Q here as Q equals lambda times L. So that is what we will substitute for Q over here. I write negative E into A equals lambda times L over epsilon naught. So we can rearrange to write in terms of lambda as lambda equals negative EA epsilon naught over L. Now A here is the area of the curved surface. And for a cylinder, we know that the area of curved surface is equal to 2 pi RL. So we rewrite for A as 2 pi RL, and that gives me lambda equals negative E 2 pi RL epsilon naught over L. We can cancel off the L from the top and the bottom, and we get lambda equals negative E 2 pi R epsilon naught. Now let us substitute these values to solve for lambda. E is given as 1.23 times 10 to the power 3 into 2 pi. R is 0.5 and epsilon naught is a constant which is 8.85 times 10 to the power negative 12. And when you solve this, you get lambda to be equal to negative 3.420 times 10 to the power negative 8 coulomb per meter. So this is my charge distribution lambda. Since it is linear charge density Q over L, the unit of this charge distribution will be coulomb per meter. In part B of the question, we need to find how many electrons per unit length are on the wire. We know that the total charge and the number of electrons are related by the expression Q equals N into E. And I want to find the number of electrons per unit length. So we can divide both sides by the length L and you get Q over L equals N over L into E. N over L, which is the number of electrons per unit length, I will write it as capital N. And we know that Q over L, which is charge per unit length, is nothing but the line charge density lambda. So we will rewrite this expression as lambda equals N into E. So we will solve for N as lambda over E. So lambda we calculated from part A to be equal to negative 3.420 times 10 to the power negative 8 coulomb per meter over E is the elementary charge and E for electron is negative 1.602 times 10 to the power negative 19 coulomb. Substitute that here minus 1.602 times 10 to the power negative 19. And when you solve this, you get the number of electrons to be equal to 2.135 times 10 to the power 11, which you can round off to 2.14 times 10 to the power 11 electrons. Let's discuss another problem based on line charge distribution. We have concept check 2.12 here. The question says a total of 1.45 times 10 to the power 6 access electrons are placed on an initially electrically neutral wire of length 1.13 meter. What is the magnitude of electric field at a point at a perpendicular distance of 0.401 meter away from the center of wire? Assume that 1.13 meter is close enough to infinitely long. So let us first write down what is given to us. We have the number of electrons n, which is 1.45 times 10 to the power 6. And then we have the length of the wire, which is 1.13 meter. And we have the perpendicular distance of electric field from the wire, which we take as r, 0.401 meter away from the center. We need to find what is the magnitude of electric field. Now for an infinitely long wire, when you use Gauss's law, you get the electric field at any point perpendicular to the wire to be equal to lambda over 2 pi r epsilon naught, where lambda is the line charge distribution and r is the perpendicular distance of the point from the wire. So if you remember this equation, you can directly apply this to solve problem. And if not, you can always arrive at this equation like how we did in the previous problem. So let's substitute to solve for E. I don't have the value for lambda, but they have given me the number of electrons. We know the charge Q can be given as N times E, and the relationship between charge Q and lambda is lambda equals Q over L, which you can write as N times E over L. I will substitute this value of lambda in the equation for E here. So we write E equals, in place of lambda, we write N E over L, and then the rest of the term, 2 pi r epsilon naught. Now substitute. Access electron is 1.45 times 10 to the power 6. E is the elementary charge, which is 1.602 times 10 to the power negative 19 over the length of the wire, which is 1.13 meter, into 2 pi. The perpendicular distance from the wire is 0.401, and epsilon naught, which is 8.85 times 10 to the power negative 12. And when you solve this, you get electric field at that point to be equal to 9.21 times 10 to the power negative 3 Newton per coulomb.